Okay, exploring quadratic relations, graphing. Let's take a look at the example of the mini golf example in exercise 6.1 on page 322 in the textbook. So if you have your textbook here, you can turn to page 322 and you'll see that example. After the ball is hit, it travels up and then back down, right? Because what goes up must come down. The distance the ball is away from the starting point can be given by the quadratic relation y is equal to negative 2.5x squared plus 6x, where y represents the blank in blank. So what's the y value? When that ball goes up and back down. Does it say anything on the graph? What relation we're graphing? Ball is hit, and what do we measure? So further along, where x is the time and y, so the distance of the ball from its starting point in meters, right? So that's what we're going to fill in here. So y represents the distance in meters, and x represents the, what's x? Time in seconds. That the ball travels. Okay, so we have time running along the x-axis and distance going along the line. Graph the relation in the graphing calculator with an appropriate window. Sketch the graph below. Label the axis, etc., etc. Okay, so I'm just going to pause for half. Okay, so turn on the calculator. Let's get rid of that. So we're going to go to y equals. Really? Seriously? Okay, we're going to go to y equals, and we are going to type in negative 2.5. So that negative is the negative at the bottom. It's this guy here, right? It's not. That's a minus sign. We don't want the minus sign. We want negative 2.5 x. That's up here. Squared plus 6x plus 6x. And let's say we just hit graph. So if our calculator is sort of been newly cleared or whatever, you've got a window which goes from negative 10 to 10 on the x's and negative 10 to 10 on the y's, and you can sort of say, well, wait a sec. If I'm hitting a golf ball, it doesn't make any sense to have negative time, right? So we'll start the x at 0. And, well, how far out should we go? So this is like 1, 2, 3. So maybe 3, right? Because it's going to come down and it's going to, hit the ground, or the distance it traveled will be back there. And how high does it go? Well, let's say we go to 5. So we're going to set our window. Not on the board, apparently. We're going to set our window. So it doesn't make any sense to have a negative x value because that's time. And we don't need to go to 10 seconds because it's apparently in 3. And we don't need to have a negative distance. That doesn't make any sense either, right? So we saw what the graph looked like, but in the context of the question, we only want a piece of the graph. And we only want that piece that's in the first quadrant. So we're going to put a 0. Oops. I'm going to put a 0 in for y min. Hang on. 0. Ah. I could do it on the board. Oh, wait. Window. If you're following along with the video at home, don't do this. Okay, 0, and I think 5 is high enough, and graph. Okay, there, nice graph, right? It fills the window. There's still a little space around the edges so we can see the whole thing. So what have we got here? We have our window going from 0 to 3 by 1s. And we have our window for y going from 0 to 5 by 1. Now this is how we describe the x window and the y window, right? And the way it works is, when we say x, this is the x min, this is x max, and this is x scale. Okay, and then the same thing here, y min, y max, y scale. Okay, so if we sketch that, it looks like this. Let's put these, there's maybe 3, 2, 1. Okay, and that's the x. This is the y. And what do we got? 1, 2, 3. So it looks like maybe 3 point something. Okay, so 3. Turn that up a bit. Okay. And if we want, we it's 1, 2, 3, 1, 2, 3, 4, 5. So what do we call the shape of a quadratic relation? That shape. Parabola, right?
Yeah.
Parabola. So the shape of a quadratic relation is called a parabola. Parabola. And we're doing these for the first couple of units, right? So we want to make sure we get down the lingo. All quadratic relations have a basic standard equation in the form y equals ax squared, so a, some number, times x squared plus some number, which may be the same but could be different, so bx plus c, where the parameters a, b, and c are real numbers. Okay? So they don't have to be integers, right? We don't even have. We've got negative 2.5, right? So it's a real number. Okay, we all good with that?
Mm-hmm.
Good. Changing the parameters and showing the effects on the graph. Let's look at a demonstration to see how changing the values of the parameter affects the graph of a quadratic relation. Answer the following questions at the appropriate time in the demonstration. Okay. Oh, hang on. Let's just pause for a second. Okay, so just to set the scene, so we're on Desmos.com. Which you can't see if you're not here. So it's Desmos, oh, I can't even write on it. Okay, hang on, I'll go back to here. So www.desmos.com. Okay, so I'm going to go here, I'm going to type in y equals ax squared plus bx, plus bx plus c. And notice here it says add slider, right? And I'm going to say add a slider for all, a, b, and c. So what that does allows me to change the values of a, b, and c just by grabbing it and sliding it along. On your graphing calculator, you would have to regraph each time, right? Like you'd have to go in and write y equals x squared. So here's what we're gonna do. We're gonna set b to 0 and c to 0. So we're starting with the graph y equals ax squared, and a is 1. So we're just starting with y equals x squared, right? The basic parabola, the basic quadratic relation. Okay, that's the basic quadratic relation, reasonably centered on the screen. It's got this point here, 0, 0. And what I'm going to do is, let's play with the a value and see what happens, right? So I'm going to take the a value so I can just take this slider. At home, you would just click on this and then just drag it along, right? So I'm going to click on this and drag it along. And what's happening to the graph? Getting thinner. Yeah, narrower, thinner, steeper, if you like. Okay. And I take a back down. And I'm going to take a into the negatives, and we're going to say, so what happens to the graph when a is negative? What happens to the graph when a is negative? Yeah, it opens down instead of opens up, right? And if I make it larger negative, what's happening to the graph? Getting thinner, right, or narrower. So apparently the larger the a value, whether it's positive or negative, we get this thinner graph. Does the basic shape change? No, it's still the same shape, right? So it's still a parabola, right? All these quadratic equations, or all these, what are we saying, are quadratic. So the common characteristics all parabola. Whoops. Okay, so let's set that back to 1. So now we know what A does, right? A affects the shape of the graph, and A affects the direction of opening, right? Does it open up? A is positive, it opens up. A is negative, it opens down. Okay, B. Come on. Okay, so what's happening with B? It's kind of moved, right? It's moving, right? It's moving it around. Is the shape changing? No. Still a parabola. Okay, so let's set B to 0 and pull it back here. And C. What's it doing here? How's it moving? Which direction is it moving? Up. And now it's moving? Down. Shape changing at all? No. Okay, so what have we got? So all parabolas have that shape, right? Sort of the curvy shape. Symmetry. So symmetry is, it's symmetrical about a line running through its center, right? This point here, so they all have what's called a vertex. This point is called the vertex. So it's the lowest point if it opens up, and it's the highest point if it opens down. Okay, so that's the vertex. Let me just shake this up. So there's the vertex, there's a line that runs through the middle called the axis of symmetry. If you want to think about that, if I put a mirror on here, it would reflect, and if I looked in the mirror, I'd see the parabola, right? Because one side just is a reflection of the other in this line, which runs through the middle and is called the axis of symmetry. I'm just going to close that. So symmetrical. About a line, about a, well, it's an up-down, it's a vertical line, right? So symmetrical about a vertical line. Passing through the vertex. What are the common characteristics? They have the same shape, same basic shape. Okay, and let's just sort of sketch one out. They have a point here that's called the vertex. Okay, so it's where they turn around, right? I mean, it's going one way, you know, it's going up and then it turns and it's heading back down, or it's coming down and then it turns and it comes back up. Were all of them functions? So all the ones I played with the A, B, C, did it ever not become a function? So they were all functions, right? For every x value, there was only one y value. For all the quadratic, yes. What is the degree of the equations? What degree were they? So we did this, right? On the other one. We talked about degree. We talked about degree? Yeah, we talked about degree. So what degree are all quadratic relations? 2. Degree 2. Yeah, exactly. So they are all degree 2. What is the degree equation of all 2? So that's characteristic. Every second degree equation, every equation of degree 2 will be a parabola, will open up or down depending on the value of A, will be symmetrical about a line, vertical line that runs through its middle, in the middle of the parabola, it's called the vertex. Okay. This line here is called the axis of symmetry. So the vertical line, it's called the axis of symmetry. Right, move on. only the parameter a is changed, what effect does it have on the graph? Okay, so we took a and it made it narrower. So it makes it narrower as a increases in value. What else does a do? Flips it, right? So reflects it. So if a is positive, it opens up. If a is negative, it opens down. So if a is greater than 0, it opens up. If a is less than 0, it opens down. So a controls kind of the shape, and the shape as in how, it's always the same shape, but how steep it is, or how wide or narrow it is, and also the direction of opening. If we only change the parameter b, what effect did it have when we changed b? Just move the vertex, right? So moving the vertex. And when c was changed, what did it do? It went up or down, right? So if c was greater than 0, it moved up. And if c was less than 0, it moved down. Right? And one way to think about that is when you put the x value in and you do the whole ax squared and bx, and so the a is kind of determine which way does it open and how narrow or wide it is, and the b sort of moves it a little bit. Once you've done that, if you take that vertex, if you add a number on the end, so I add 10, then it's going to move up 10, right? So that's what c does. It moves it up or down. So if c is greater than 0, moves up. If c is less than 0, moves down. Okay, and I'm not going into great detail on the b value just because it's really hard to look at that and sort of say, like I can predict, if c is 10, I know it moved up 10. If b is 5, I can't really say, well, it moved that many, this much that way, right? It's just got a more profound effect on it, so. If the equation of the parabola is written in the form y equals ax squared plus bx plus c, then the parameter blank is the y-intercept of the parabola. Yeah, let's go look here. So here, c is 4.1. Let's see, 4. Go away. Damn it. Hang on. I'll do it on here. There. C is 4. Let me move b a bit. What's the y-intercept right now? Where's it intercept? 4. Okay, has it changed because I'm changing the b? Okay, what if I change the a? Is the y-intercept changing? So which parameter is the y-intercept? Which parameter is the... What did the y-intercept just change to? What did the y-intercept just change to? Yeah, so the parameter that's the y-intercept is c. Okay, tell me about the y-intercept. If I say y-intercept and you say the y-intercept occurs when? When the x value is equal to 0. So if we have ax squared plus bx plus c and I make x 0, what happens to this term? What happens to this term? So all we're left with is the y-intercept, which is c. So the parameter c is the y-intercept, right? Because the y-intercept occurs when x is 0. If I make x 0, the ax squared term, that's 0. The bx term, that's 0. All I'm left with is y equals c. See? predicting values of parameters. For each of the parabolas below, predict the values for the parameters b and c if the equation for each parabola can be written in the form y equals x squared plus bx plus c. Write the equation, check your answers with the graphing calculator by entering the equation and choosing the windows to match the grid. Okay, so I'm not necessarily going to choose the window to match the grid, and I'm not going to do it on the graphing calculator, right? Although, keep in mind, you have to know how to use the graphing calculator because that's the thing you get to bring with you to the test, and that's the thing that you get to use on the final exam, and that's the same deal in 30-2, right? Or 30-1, you know, if you go on to that down the road, all you get to use on test time is the graphing calculator. But for exploring this stuff, you know, we can use this. So I'm going to set A to 1, by actually going up here and typing in a 1. Okay, and okay, I didn't want to do that. And let's just here, we'll set B to some other value. Okay, so hang on, let's go here. What's the value of, okay, so ax squared. So how do you know that A is equal to 1? Right? So I want you to think about this. Let's go back. I'm going to go back to the basic parabola. So I'll set B and C to 0, and we'll just take a look at some of the characteristics here. Okay. So what is it? And here, I'm going to move this. Actually, I'm going to put this away. So we're looking at y equals ax squared, right? 1x squared. No b is 0, c is 0. Okay, I'm going to move this here so we can see a little bit more. So this is your basic quadratic function, your basic parabola, y equals x squared. And so if x is 0, 0 squared is 0, right? 1 squared is 1. So you put in an x value of 1, you get a y value of 1. 2 squared is 4. 1, 2, 3, 4. 3 squared is 6, 7, 8, 9. Negative 3 squared is, negative 3 quantity squared is 9, right? Now remember, it's symmetrical about, in this case, it's symmetrical about the y-axis, right? So if I move 3 units away from the y-axis here and go up 9, then if I move 3 units this way, right, to the left of the axis of symmetry, how far up do I have to go? 9, right, because it's symmetrical. Okay, so you've got 3, 9, you've got negative 3, 9. You've got 4, 16, which we can't quite see because it's just a little bit off. Okay, but if I want to get the A value, then I know that if I don't mess with A, then if I move 1 unit away, I should move 1 unit up, right? Because 1 squared is 1. So if I look at the vertex and go 1 unit from the vertex and go up, now here, let's play with this a little bit. So let's say I make A 2. Okay, so now I've moved 1 unit away. How far up am I going? 2. Because what are we doing, right? We're saying, okay, let's remember order of operations, right? You got to square the x value. So let's square 1. 1 squared is 1. Then we're going to multiply by A. So it's 1 times 2 is 2. So if I move 2 units away, and normally I would go up 4, but now it's 2x squared, how far up do I go? So what do I have to do? I took the 1 and I doubled it, made it 2. I take the 4, it's going to become 8. 2, 3, 4, 5, 6, 7, 8. Right? And I think we can actually trace along here, right? And we can see, oh look, there's the point 2, 8. Okay. If I went 3, how far up would I go? So normally it's how far? 3 squared is 9, but I've got the 2 in front, so it becomes, say it loud, 18. What if I change A to 3? Okay, so normally we move 1 unit from the vertex, we go up 1 unit, but how far up are we going to go now? 3. Normally I move 2 units. 2 squared is 4, but how far up do I go now? 12, right? There's the point there. 2, 12. Okay? So that's what A is doing. So when I go look at, and I'm going to set A back to 1 because we're supposed to just be doing AX squared. But what I wanted to show was, how do I know what A is? Okay, I move 1 unit, I go up 1, A is equal to 1. How did it get down to -2? Which coordinate affected the y-intercept? C. So what's C? -2. What do you think B is for this? Okay. What did B do? It moved it, right? Does that look moved? No. It only moved down, so what's B? 0, right? No movement. If there's no side to side, right, what does this do? Changes the shape, tells me which way it opens, right? So it makes it narrower or wider. Well, in this case, how do I know if it's narrow or wide? I go over 1, up 1. I go over 2, 1, 2, 3, 4. I go up 4, right? 2 squared is 4. If it goes up 4, then the A value is 1, right? If it goes up 8, I know the A value is 2. If it opens down, I know the A value is negative. If it's moved left or right, I know there's a B value, and if it's not moved left or right, then B is equal to 0. Okay, this one, from the vertex, I go over 1, up 1. I go over 2, 1, 2, 3, 4. What's A? 1. Go over 1, up 1, right? That's the normal, that's the unstretched, right? A is a stretch factor, right? It stretches it up or down, right? Yep.
I'm just confused, like, how we know, like, what A, B, and C are.
Okay, so A from the shape, right? So A, I start at the vertex and I say, if I move 1 unit from the vertex and this thing has not been made narrower, right, then its basic shape means that I should go up 1. Over 1, up 1, A is 1. If I went over 1 and up 2, then I would say, well, normally when I go over 1, I should go up 1, but I'm going up 2. That means A is 2.
So do you do that
From the vertex.
so whenever, so if you want